Hello everyone, welcome to GatePass. In this video, I am going to check problems related to thermodynamics that appeared in Chemical Engineering GATE paper of 2010. First problem which I am going to take, it talks about a binary solution at constant temperature and pressure, and its molar density rho is given as a function of mole fraction. Now they have asked you to calculate what will be the partial molar volume of component 1 at infinite dilution. Okay, so in last video you have seen that the partial molar property at infinite dilution we represent it with a infinity sign over here. Okay, so now up till now you have seen problems in which partial molar properties were given and you had to find your mixture property. Okay, for that you used your summability relation. So how do we write our summability relation? If M is any property, then I can write x1 m1 bar plus x2 m2 bar. So for a binary solution, my summability rule usually takes this form. Okay. Apart from this, there is one more equation which is very important. That is your Gibbs-Duhem equation. And for at constant temperature and pressure, I can write x1 dm1 bar plus x2 dm2 bar, that is equal to 0. So these are two important equations and you should remember them. Okay. Our problem is now, if the mixture property is given, how do we find our partial molar properties? So that is what we are doing right now. So let me write my summability relation. Okay. Now if I take a derivative of this equation, get dm, that is equal to x1 dm1 bar plus x2 dm2 bar plus m1 bar dx1 plus m2 bar dx2. Okay, this is what I get. Now what you observe over here is that x1 dm1 bar plus x2 dm2 bar, that is equal to 0 from your Gibbs-Duhem equation. Okay, so what you are left with is dm is equal to m1 bar dx1 plus m2 bar dx2. Now since this is a binary solution, so I know that my dx1 is equal to minus dx2. Okay, so instead of dx2 I can write minus dx1, so that's what I will do. Now since dx1 is common, what I will do is I will take out dx1 common. So m1 bar minus m2 bar dx1, that is equal to dm, or if I take a derivative over here, dm by dx1, that is equal to m1 bar minus m2 bar. Okay, so this is one equation which we will use. Fine. Now I will go back to my summability relation. Now I have to find my m1 bar for this equation. So what I will do is I will eliminate x1 from this equation. How do I do it? I will write m, that is equal to 1 minus x2 m1 bar plus x2 m2 bar, which I can write as m1 bar minus x2 m1 bar plus x2 m2 bar. Okay, so x2 I can take common outside, and what I am left with is m2 bar minus m1 bar. Okay, so I will take it as minus and I will write it as m1 bar minus m2 bar. Okay, now I know that m1 bar minus m2 bar is nothing but your dm by dx1. Okay, so I will put that value. So m is equal to m1 bar minus x2 dm by dx1, or I can solve this equation for the partial molar property of component 1. So this will give me m1 bar, that is equal to m, that is the mixture property, plus x2 times dm by dx1. Okay, so this is the formula which we are going to use right now. So now you have the equation which relates the partial molar property of component 1 with the mixture property. Okay, so now let's go back to the problem statement and see which property we have to find out, that is your partial molar volume. Okay, But realize this, that your molar volume is nothing but your inverse of the molar density. Okay, so your V is equal to 1 upon rho. So I can write now this equation as, in terms of V, I can write it as 1 plus x2. Let's write down the equation, okay, in terms of V. So I have to find out first my partial molar volume of component 1, and that will be equal to mixture volume, okay, that is your molar volume, okay, plus x2 times dV by dx1. Okay, that is what you have to find. Now let's put in the values of V in terms of your mole fractions. So I am going to do that. So V1 bar, that is equal to 1 upon 1 plus x2 plus x2 times d by dx1 of 1 upon 1 plus x2. Okay. Now let's change the variable x2 into x1. So what you get is x2 is equal to 1 minus x1. So this will become 2 minus x1 plus 1 minus x1 d by dx of 1 upon 2 minus x1. Okay. This derivative is very simple. Do it. So you have, this term will come as it is, plus 1 minus x1. Now take the derivative of 2 minus x1. What you get is 1 upon 2 minus x1 square, and it will be multiplied twice with minus 1. Okay, so that will cancel. Now in this form you have to find out what? V1 bar infinity, that is the partial molar volume at infinite dilution. So I am not going to solve it further. I will just directly put over here my value of x1 tends to 0. So it will be 1 by 2 plus 1 minus 0 is 1. Okay, this will become 1. So 1 upon, this is 2 whole square. So it will be 1 upon 2 plus 1 upon 4. So that will be equal to your 3 upon 4 or your 0.75. Okay. So the answer which you have obtained is that your partial molar volume of component 1 at infinite dilution is 0.75. Okay. So the next problem which I am going to take, it relates to throttling process. Throttling we have seen in detail a couple of videos back. You can go and check that video. Okay. Now in this problem they say that you have a saturated liquid at pressure P1 and T1 which are given, and they have an and it has an enthalpy of 750 kilojoules per kg. Okay, it is throttled toward temperature and pressure which are given as over there T2 and P2. Fine. Now it says that at the exit conditions there is a liquid vapor mixture. So to start with you have a saturated liquid. After throttling you get a liquid vapor mixture. Okay, let's say that the fraction of this mixture which is vapor, let's denote it by x. So x is your fraction vapor. Okay, fine. Now in this question they have asked you to calculate what is the percentage of the original liquid which has vaporized. So ultimately you have to find out what is the fraction of the vapor in the exit stream. From that you can calculate the percentage. Okay, 4 options have been given. You have to choose which one is the correct one. So let's see this problem. It's very simple. As you know, throttling is an isenthalpic process. So your inlet enthalpy should be equal to your outlet enthalpy. So I know right away that my H2 that should be equal to 750 kilojoules per kg. Okay, if I know my H2 now, I can relate it to the specific enthalpies of the saturated liquid and saturated vapor. Okay, and how do I write it? Okay, I will make use of this mass fraction which I have defined. Okay, so x is the fraction of vapor in the exit stream. Once again I am telling you, so I am going to write x times HV plus 1 minus x times HL. Okay, so now my H2 is 750, that is equal to x times HV is 2500 plus 1 minus x times HL, that is 500. So I'm going to solve this equation for x. If I solve this for x, I get a value of 1 by 8. Okay, so the fraction of the liquid which has vaporized is 1 by 8. You have to convert it into percentage. So how do you do it? So percentage vaporized, that will be equal to, just multiply the fraction by 100 and you get what? 12.5%. Okay. So your option C is correct. So what you observe in this is that you just needed two basic facts. First, throttling is an isenthalpic process. So H1 is equal to H2. And then if you have H2, how do you write this equation? You all know it's a very familiar equation. Okay. And it was a simple problem. You can solve it within 2 minutes. So next, let's move on to another problem. So the next problem is question number 16. Once again, we see that this is a problem based on Raoult's law. In fact, in the problem statement itself, they have said that assume that Raoult's law is valid, find the value of y1. So you have an equimolar mixture of component 1 and 2 in equilibrium with its vapor at 400 Kelvin. So what information they have given? That your x1 is equal to x2, that is equal to 0.5. Okay, and the saturation pressures at 400 Kelvin of component 1 and component 2 are already given. Okay, and they have said that use Raoult's law and find out y1. So we have done these type of problems so many times, so quickly we are going to do it. Write down the Raoult's law for first component. So y1p, that is equal to x1 p1 saturation, y2p, that is equal to x2 p2 saturation. Okay, add these, you get p is equal to x1 p1 saturation plus x2 p2 saturation. Okay, we have to find out y1, put the value of p over here. What you get is y, that is equal to x1 p1 saturation upon x1 p1 sat plus x2 p2 sat. Since x1 is equal to x2, it will cancel out throughout. So what I have is p1 saturation, that is, so what we have is p1 sat divided by p1 sat plus p2 sat. Very simple problem. p1 sat is 180. p1 sat plus p2 sat, 180 plus 120, 300. So 180 by 300, that is equal to 0.6. So your option D is correct. Okay. Very simple problem. You have seen it so many times. So the next problem which I am going to take, it talks about a new linear temperature scale which has been defined and denoted as degree S. The freezing point of water on this scale is 200 degree S and the boiling point of water is 400 degree S. Now they have said that what will be 500 degree S on Celsius scale. Okay, 4 options have been given to you and you have to tell which one is correct. Fine. So it's a very simple problem. What I do is that, since this is a linear temperature scale, okay, let's plot a correlation plot, okay, between degree C and degree S. So 0 degree on Celsius scale, it corresponds to 200 S, and your 100 degree, that is your normal boiling point of water, it corresponds to, let's say, 400 degree S. Okay, fine. So since your new temperature scale is also linear and your Celsius scale is also linear between 0 and 100 degree, I am just going to draw a straight line as my correlation. Okay, now I have to just find out the equation of this line which will give me a correlation between S and C, and that's what I will do. Okay, so if I have any point in between which I denote as S and C, okay, then I can write a 2-point formula between this. I can say S minus 200 upon C minus 0, that is the slope of this line. Okay, that should be equal to the slope of the entire line, so that is equal to 400 minus 200 upon 100 minus 0. So S minus 200, that is equal to 200 by 100 is 2, so that is 2C, or what you have is S minus 200 upon 2, that is equal to C. So any temperature on your degree S scale that can be converted to degree centigrade. So if you have S that is equal to 500, so 500 minus 200 is 300 divided by 2 150. So 500 degree S will correspond to your 150 degree C. It was a very simple problem. So in this video we have taken all the 4 problems that appeared in year 2010 related to thermodynamics. I hope you liked my teaching, and if you find these videos useful, please don't forget to subscribe to my channel and hit the like button. And thanks for watching.